Today's topic is fuel cell, in particular the solid oxide fuel cell, which is supposed to be sorry, which is supposed to be the all ceramic fuel cell and a very important area of application for advanced ceramics. It is in the energy sector, environment and energy sector, and let us try to discuss the materials used, the principle, and why this particular topic is so important to us. So, we will be discussing the solid oxide fuel cell, and first of all we must know what is a fuel cell. That is quite obvious. The fuel cell is an electrochemical cell. It is an electrochemical device which generates electrical power continuously, as a gaseous fuel is electrochemically burnt in a continuous manner. So, as the name suggests, there is a fuel which is burnt, not normally burnt, it has its own calorific value no doubt, but it is burnt in an electrochemical system, and therefore, it is generating a power, generating a voltage, and of course, you can also draw some current through this. So, it becomes a power system or a conversion device, energy conversion device from the fuel energy to the electrical power. So, that is what we know about fuel cell. In short, what are the characteristics of a fuel cell? As has been mentioned, it is an electrochemical device, generates electricity, requires a continuous flow of reactants. As you have mentioned, we will have a fuel and that will be oxidized and that will be burnt electrochemically. So, two reactants are necessary. One is the fuel, a gaseous fuel, of course not a solid fuel in this case, it can only take up gaseous fuels, and a oxidant, normally air. Uses pure hydrogen gas or hydrocarbons as the fuel. So, depending on the particular type of variety of fuel cell, it may use hydrogen or hydrocarbons which can be burnt electrochemically. The use of hydrocarbons may require a reformer. Ultimately, the hydrocarbon has to be catalyzed, or it has to be dissociated into a mixture of hydrogen and carbon monoxide or some other hydrocarbon. So, that part is done by a device called reformer. So, when although hydrocarbons can be used in principle, but ultimately it has to be converted into hydrogen for certain variety of fuel cells, but in other variety one can also use carbon monoxide. Basic fuel cells contain an anode, cathode and electrolyte as shown here. As it is mentioned, it is an electrochemical cell. So, we have to have a anode, an electrolyte and a cathode. Well, we have discussed earlier the very principle of a oxygen ion conductor and measurement of oxygen partial pressure. Okay. So, the same principle applies when you talk about solid oxide fuel cell. In particular, we will be discussing few other fuel cells, but this principle or the Nernst equation in this case, it basically applies to the solid oxide fuel cell, but very similar thing also applies to other fuel cells. So, the same equation, we have a electrolyte in between. Incidentally, it is an oxygen ion conductor here, and you have partial pressure, one partial pressure on the other side, or the chemical potential of the oxygen, and a different chemical potential on the other side, and therefore, you will get an EMF. So, this was used in connection with the oxygen sensor using a zirconium dioxide. The basic principle is same. So, instead of just measuring the open circuit EMF, we can draw some current through that, and that is what is called the fuel cell. So, we can use the same thing as a source of power. Well, we can have a look at it, the history of fuel cell. It is not a very recent concept. The concept is as old as 150 years old, and the fuel cell was first demonstrated in 1839 by Sir William Grove, who tried to reverse the phenomena of water splitting by applying electric field and to generate hydrogen and oxygen. So, by that time the splitting of water was known, and Sir William Grove tried to think, if by supplying electricity one can generate hydrogen and oxygen, is it possible to reverse the reaction and combine hydrogen and oxygen to get the electricity. That was his idea, and that is he actually was successful in doing that. He termed the device as gas voltaic meter, a battery. So, by that time basically he was working on battery, so he termed it as gas voltaic battery, but the term fuel cell was coined much later in 1889 by Ludwig Mond and Charles Langer. So, that was one part of the history, and then fuel cell was first put to use in 60s in the last century, 1960s, to provide electricity on board the Gemini and Apollo spacecrafts. So, one of the reasons why fuel cell was used, because its power to weight ratio is very high. So, you can, from the same weight, per unit weight, one can generate much larger electrical power, and therefore, one can use this on spacecrafts where the weight is an important criteria. During the 1970s, the fuel cell technology was developed for systems on Earth. Okay. Looking at the success of the space missions, Gemini and Apollo spacecraft missions, people found that yes, the technology can it be used on Earth also for our own purposes, because there is a shortage of fossil fuels, and whether it can be an alternative source of fuel, an alternative source of energy. So, that was the first time in 1970s people started developing a commercial way. Of course, the commercialization is still to be achieved, but a very strong research activity went in for developing power systems based on fuel cells. Then during 1980s it began to be tested for the purpose of utilities and automobile sector particularly, because the idea of running an automobile with electrical power or battery power was still on, but it was not successful because the power to weight ratio of normal lead acid batteries are very high or very low in a sense. So, it was not very commercially successful. So, with the research activity or the development of fuel cell, one could think that a captive power stations, either a captive power station or a automobile can be run with these kind of power systems. So, that is the history. Still the research is going on in a very active manner, and but it is a power source basically. So, another kind of power source as mentioned is battery. Okay, battery is also a source of power, electrical power in a small way, and fuel cell is also a very identical or a analogous way one can generate power from the fuel cell as well. So, can we have a look at what are the differences between a battery? It is not actually a battery, it is a different kind of power system, and these are the characteristics of the battery as well as fuel cell. Battery generates power electrochemically. In fact, both of them generates power electrochemically, both of them are electrochemical cells. Electrodes in battery are working materials, whereas working materials in the sense the electrode itself is a actually source of the energy. So, certain amount of certain chemicals or metals are used as the electrodes here. Whereas, in case of fuel cell one cannot do that, because basically the reactants are gases. So, gases as such cannot be used as a current collector or a contacts. So, one needs a different kind other materials. So, the gases are the working electrodes, working materials, and therefore, we need an additional set of materials to act as a electrical contacts or current collectors. In case of battery, electrodes get consumed, whereas in case of fuel cell the electrodes do not get consumed. If we assume that the reactants, the hydrogen or the fuel as well as the oxidant are actually the electrodes, they do not get consumed. Sorry, I am sorry, it is not like that. The electrodes are actually the contacts. Here it is said the electrodes are the contacts. So, the contacts do not get consumed, it is the reactants, the fuel and the oxidant which gets consumed in a continuous manner. The basic electrodes remain same. Electrodes in the sense here we are talking about the contacts and the current collectors. Limited operation, because as long as particularly in a battery as long as the chemicals are available it will produce power. Once the chemicals are consumed and converted to a different kind of products, then the source of power is lost. So, the power will not be available anymore. In case of fuel cell, one can get continuously generate power as long as one can supply the fuel and the oxidant on two sides of the fuel cell. So, one becomes the cathode, another becomes the anode. So, one can say here you have supplying air from one side and the gas from the other side, and this is the system in which the power is getting generated. So, this is one electrode and that is one electrode, but the actual the working electrodes are actually the air and the oxygen or the fuels hydrogen or carbon monoxide. It is basically a battery is basically a storage device. Okay, it stores the energy, chemical potential and the chemical energy, and which can be converted on site into a electrical power, whereas this is a conversion device. Okay, it is basically a conversion device. It does not store the power because the chemicals, the source of energy is outside the system, whereas in a battery the source of energy is within the system. So, that is the differences between a battery and a fuel cell, although both of them are basically an electrochemical devices. Well, based on these principles, we have several types of fuel cells. They are termed in this manner: alkyl fuel cell, direct methanol fuel cell, that primarily depends on either the electrolyte, kind of electrolyte used, or the kind of fuel one use in these cells, or a phosphoric acid fuel cell. They are in short talk, the terminology is AFC, DMFC, PAFC, or proton or polymer exchange membrane fuel cell. Polymer exchange membrane fuel cell is PEMFC. Okay. Molten carbonate fuel cell, and finally, the topic of our interest as ceramists or under the course of advanced ceramics, our primary interest is here, solid oxide fuel cell. I will give you some characteristics of this. This particular one is called alkaline fuel cell, because it alkali, some form of alkali, liquid alkali is actually the electrolyte here. Okay. That is why it is called alkaline fuel cell. The direct methanol fuel cell, although we have been talking about in other cases, it is the hydrogen, the fuel is hydrogen or carbon monoxide or a mixture of them, but methanol can also be directly oxidized in some of the fuel cells, and one can get energy out of it. So, because the fuel is methanol, so it is methanol fuel cell, direct methanol fuel cell, not hydrogen or gaseous fuel cell, it is actually a liquid fuel cell. A phosphoric acid fuel cell has been termed because once again the electrolyte, just like here alkali is the electrolyte, here acid is an electrolyte. So, phosphoric acid is used as the electrolyte here, and obviously the charge carriers here is the hydroxyl ion, whereas the charge carrier here is the hydrogen ion. Okay. So, this is a liquid acid which becomes the electrolyte here. Proton or the polymer exchange membrane fuel cell, just like phosphoric acid fuel cell, here is also a hydrogen ion conductor, but this is not in the liquid form. This is a polymer, a particular polymer which is having a sufficient amount of hydrogen ion conductivity, and that is used as the electrolyte. So, here compared to phosphoric acid, this is a solid electrolyte, but both of them, the conducting species or the charge carrier is basically hydrogen ion. So, the protons are the basic charge carriers and one can make membranes. In fact, the electrolyte in this case is called the membrane because it preferentially allows hydrogen ion to pass through. Then there is another type of fuel cell where electrolyte is once again liquid, but at a sufficiently high temperature, fairly high temperature, about 600 to 800 degrees centigrade. So, this is a carbonate, liquid carbonates, and that carbonate ion is the charge carrying species, and this is a high temperature, a moderate temperature, I can say moderate temperature fuel cell where molten carbonates are normally used as the electrolyte. The operating temperatures of these things are at different temperatures. This is more or less room temperature, these are again slightly above room temperature. I will give you some temperature range, but they operate at different temperature ranges. And solid oxide fuel cell is once again a all solid state device where the electrolyte is a solid, the electrodes are also solid, and the fuel is only gas. So, the fuel is either hydrogen, carbon monoxide, or some hydrocarbons like natural gas, mixture of hydrocarbons like natural gas and so on. It can be used quite easily. One of the reason is it operates at a fairly high temperature. Originally it used to operate around 900 to 1000 degrees centigrade, primarily because the electrolyte zirconia does not have very high ionic conductivity, or the overall conductivity is relatively low. So, sufficient conductivity is obtained only at a higher temperature. Okay. So, that is the reason this is the kind of operating temperature is highest among all the fuel cells listed here. Of course, there is a tendency to the research is going on to reduce the operating temperature, we will look at it. So, this is a all solid state fuel cell and all ceramic fuel cell. So, all the components are ceramic components and they must withstand fairly high temperatures. So, our topic of discussion is primarily concentrated, will be concentrated on the solid oxide fuel cell. Well, advantages of fuel cells in general are as follows: high efficiency, we will explain why it is high efficiency, the conversion efficiency, the chemical to electrical energy conversion efficiency is extremely high, in fact higher than any other system one can think of. Fuel diversification, that means in some of the fuel cells, not all, there are different kind of fuels can be used, although they are all gaseous fuels except in DMFC, all the gaseous fuels, but different kind of either hydrogen can be used, carbon monoxide can be used, or a mixture of hydrogen and carbon monoxide, or in some cases hydrocarbons can be directly fed into the system. So, one can have different kind of fuels, but the most important characteristics is its high efficiency. Zero emission and silent, well, compared to many other mechanical systems like generators, gas generators and so on, or steam generators, you don't have a moving part here. You are it's basically a stationary system, except for gas supply and air supply. You need some blowers and so on, but otherwise the basic system is stationary. You do not have a moving part. That is why it is also silent, but zero emission, that is another very important. Zero emission in the sense, here we are basically talking about carbon dioxide emission, provided of course one uses hydrogen as the fuel, because when hydrogen gets burnt, it actually the products of combustion is nothing but H2O. So, we do not generate carbon monoxide or carbon dioxide, that is one environmental issue. Other emission is there is no particulates. If you are talking about a thermal power plant where solid fuel is burnt, you generate huge amount of particulates, okay, particulate emission, and that emission is not there in this case. So, we can say it is a zero emission. So, it is a basically a clean energy system. It is a clean energy system, environmentally benign system, and those are the reasons why fuel cell research has become a very important and fascinating in these days. Enabling technology, because it gives you some other technology. For example, fuel cell technology is also giving you to automobile research, because how the fuel cells can be used in battery operated or electric vehicles. Electric vehicles is another area where fuel cell or that dependent on the fuel cell technology development. So, these are some of the advantages, but most important advantage is high efficiency. That means the conversion efficiency. Most of the chemical energy of the fuel is converted into electricity or electrical power. Well, we will do that. So, of course, finally, as I mentioned, I have explained that it is a clean and efficient energy conversion device. So, when you are talking about environmental pollution, and also we are talking about the carbon economy to the hydrogen economy, that means we have to burn or generate less of carbon dioxide in the environment. This is one of the techniques by which one can reduce carbon dioxide in the environment. This is the reason why it is more highly efficient system of energy conversion. If you are talking about a thermal power plant, then the chemical energy of the solid fuel coal is first converted to thermal energy, because it is normal burning to generate thermal energy. So, that thermal energy generates steam, and that steam again goes to the steam turbine and generate electricity. So, it goes through a large number of conversion steps. So, directly chemical energy is not getting converted into the electrical energy. So, at each step there will be a lot of loss, and therefore, the overall efficiency is not very high, only 30 to 35% of the chemical energy is basically converted to the electrical energy, and 65 to 70% is actually lost. So, it is a huge loss so far as when you are talking about the power generation. Whereas, if you talk about a fuel cell, it is an electrochemical conversion, it is a one step process. Okay. So, it does not go through a multiple step. So, it is a one step process of chemical energy is directly getting converted to electrical energy, and therefore, theoretically it is a very efficient process. Okay. So, of course, there will be losses because of many other reasons, but in principle it is a one step process, and therefore, the conversion efficiency has to be very high. The electrical efficiency as such can be as high as 80 to 90%, but the overall plant efficiency depending on many other features, it can come down to about 40 to 50%. We will look into that later on, why such losses take place and where exactly we lose some of the energy. But in principle, it is very high compared to thermal power plant, because both of them are basically looking at the energy generation, the conversion of chemical energy to the electrical energy. Well, these are some of the working principle of different types of fuel cells. To start with, the alkaline fuel cell or alkali fuel cell. Basically, you have two different components. One is the fuel compartment and the other is the oxidant component, either it can be pure oxygen or mostly air. You have electrodes. This is one electrode and this is another electrode. So, this is an anode and this is a cathode. So, there is interfacial reactions, and this is of course the electrolyte. Okay. So, this is the electrolyte, some kind of alkali, and that actually has OH ions which are mobile in this case. So, OH ion, because it is a negatively charged, so it is actually takes the oxygen from this side and then it goes to the other side, and then one can also look at it from the other point of view. The hydrogen here, the hydrogen actually combines with the OH. Here oxygen is actually goes to the oxygen ion and it takes up electron from here, whereas hydrogen gives the electron there. So, the electron goes to this and then this electron gives donates the oxygen atom. So, it becomes oxygen ion. So, and then hydroxyl ion moves to this and combines with hydrogen. So, and becomes the water. So, this is the reaction for alkali fuel cells, and if you have hydrogen ion or hydrogen ion is the conductor, it moves to the opposite direction, and then you have a electrolyte which may be a phosphoric acid fuel cell, a phosphoric acid as the electrolyte, or as I mentioned earlier, a polymer. Incidentally, it is a very commercially available particular very specific polymer having a very high hydrogen ion conductivity, which is called naphthalene, and that is the most efficient hydrogen ion conductor so far as the solid polymers are concerned. And then this is the source of hydrogen, and hydrogen gets ionized there, then it is become hydrogen ion, it moves to this direction, it combines with the oxygen on this side and it releases, it takes up the electron from there, and the electron moves in the outer circuit and hydrogen ion moves in the internal circuit. So, internally it is a charge carrier is a hydrogen, and externally of course there is a electron flow. So, you can generate current in the, and a load can be attached to that. So, oxygen comes from one side, hydrogen comes from the other side, and they combine electrochemically and ultimately water goes there. So, on this side hydrogen and water goes on the same side, whereas for this system oxygen and water is on the same side. So, hydrogen comes from the other side, combines with oxygen and releases water as the product of conversion. Here oxygen comes from other side and it combines with hydrogen and water is released on the same side as the hydrogen. So, there is a continuous flow of hydrogen here, there is a continuous flow of hydrogen there also, and on this side there is a continuous flow of oxygen. So, as long as these flows are maintained, you can generate electrons or you can generate current on the outer circuit, and a load can be connected to that. The particular fuel cell which we are interested in is a solid oxide fuel cell, and that is, as I said, it is all solid state fuel cell. Everything is solid here, and the electrolyte is an oxygen ion conductor. This is an OH ion conductor, this is an hydrogen ion conductor, and this is an oxygen ion conductor. So, because we are talking about a electrochemical system, so there may be possibilities of different electrolytes, and according to we choose the electrodes. So, this is hydroxyl ion, this is hydrogen ion, and this is an example of oxygen ion. So, oxygen ion is the conduction is the electrolyte conducts oxygen ion, and on this side you have anode, this is a cathode. On this side you supply air, and here it is reverse to this, because this is hydrogen, this is oxygen. So, the cathode and anode will be different. So, here oxygen or air is supplied to this, and this is get ionized on this side, and then oxygen moves there. Oxygen moves there and combines with the fuel, maybe hydrogen, carbon monoxide. So, once again the product of combustion is on the hydrogen's fuel side, and air comes from the other side, okay. And you produce a voltage here, and this is the load on the external circuit. Otherwise, the basic principle is same. The only thing, the difference here is the mobile species or the charged species of the electrolyte is oxygen ion, and they are all solid state. So, we will see what are the different materials we use for this kind of a system, but this is the basic principle by which one can generate electricity or power, electrical power from the chemical potential or the chemical energy of the fuel, of this fuel. Well, referring to the solid oxide fuel cell, we will go into the little details, the electrode reactions, charge and mass transport in SOFC or solid oxide fuel cell. Now, once again this is the schematic of the system of the cell. This is basically a what we call the electrode or the membrane electrode assembly. So, this is only a part of the main reaction site, okay, the main reaction site where you have the cathode, you have the electrolyte and the anode all in the solid state. Oxygen is moving. Now, cathode, both cathode, because you have a gaseous fuel and gaseous oxidant. So, the reaction, electrochemical reaction or the charge transfer is basically taking place at this interface, okay, electrolyte electrode interface, either the cathode electrolyte interface or the anode electrolyte interface. So, the gaseous fuel or the gaseous oxidant has to come in contact with this interface, and the triple phase boundary, that means one is the cathode, electrolyte and the gaseous environment. So, these are the triple phase boundaries like this. These are the reaction sites where this kind of reaction is taking place. The oxygen, because this is the oxygen side, the cathode side. So, the oxygen plus 4 electrons give rise to 2 oxygen O minus. So, at this interface this reaction is taking place. So, the reaction sites are very important. Higher is the reaction site, higher is the conversion, and better is the current carrying capacity or the current generating capacity. So, more electrons will be generated, and one can draw more and more current. So, it cannot be a completely dense material, it has to be a porous material. So, that through the pores molecular diffusion takes place, oxygen comes to the surface, then gets atomized and it gets the electron from this and gets ionized. So, once the oxygen gets ionized, this material, the electrolyte is specifically an oxygen ion conductor. So, oxygen, because there will be a potential difference, there will be high oxygen potential on this side and there is a low oxygen potential, because the fuel has a reducing condition, low oxygen potential. So, from high oxygen potential there is a kind of tendency of driving force. In fact, the driving force will be there for the oxygen to move from this side to that side, from the higher oxygen potential on this side to the lower oxygen potential on this side. So, oxygen ion will move along the through the bulk of the electrolyte. Now, this can move because this electrolyte has been chosen in such a way that it has a very high oxygen ion conductivity. There is no electronic conductivity in this. So, the electrolytes can be used, or electrolytes as per definition, they will have only ionic conductivity and no electronic conductivity. And so, the oxygen ion will move there and then it will combine with hydrogen in this manner. Hydrogen plus oxygen ion will generate water and then it will release electron. So, the electron will flow from this side to this load to this side and this will continue. So, that is the kind of principle what we have discussed earlier also. The only thing we want to introduce here or add is both cathode and the anode has to be a porous material. Whereas, the electrolyte has to be completely dense. So, this is one of the major requirement of this kind of a system. The membrane electrolyte assembly, one can say this compact layer can be called as a membrane electrolyte assembly. Membrane is basically an electrolyte, membrane electrode assembly, not the electrolyte. Membrane electrode assembly, membrane basically because it has a semi permeability through only through oxygen, no hydrogen can go through, no other gas can pass through, only oxygen ion can pass through. So, it is basically acting as a membrane, although physically it is a very dense material. This oxygen permeability is because of the oxygen vacancy. So, it is the lattice oxygen is going through, there is no physical pores in it. So, this electrolyte has to be completely dense, so that oxygen, molecular oxygen diffusion is avoided. Oxygen molecule should not pass through and then combined with hydrogen. If that becomes so, then it is only a thermal combustion, it is not an electrochemical combustion. So, electrical energy cannot be generated by that process. So, there should not be any porous or continuity of the pores. Okay. Even if some small pore is there, it has to be discontinuous or entrapped pores. Okay. So, this is one of the major requirements. So far as the solid oxide fuel cell is concerned, both the cathode and the anode material has to be porous material, whereas the electrolyte has to be completely dense material, and it has to be because some such material is already available with us like zirconium oxide, zirconium dioxide. We have seen earlier calcium stabilized or ETS stabilized zirconium dioxide can act as a very good oxygen ion conductor, and therefore, these are the materials one can use. We will come to that, what are the different materials possible to use either as the cathode material or the anode material. In case of carbon monoxide, this is again a very similar reaction takes place. Instead of hydrogen, one can have carbon monoxide and then oxygen and carbon dioxide. So, it again releases 2 electrons here. So, whether it is the fuel is a hydrogen or carbon monoxide or a mixture of them, these are the oxidation reaction which is taking place on the anode side, and there is a ionization of oxygen ion on the cathode side. Okay. So, there is a very high oxygen potential on the cathode side, whereas there is a very low oxygen potential on the anode side, and this is a highly reducing condition, and this is a highly oxidizing condition. So, this is also another requirement of this electrolyte, because on one side of the electrolyte is a very high oxygen potential, very high oxidizing condition. On the other side is a very high reducing condition, because hydrogen is a highly reducing. Okay. So, this electrolyte must be thermodynamically stable both at high oxygen potential as well as low oxygen potential, otherwise this material will get reduced or oxidized. So, there will be non-stoichiometry set in, because many of the oxides in presence of hydrogen can reduce to its corresponding metal. So, one has to choose a particular electrolyte which should not be reduced even in presence of hydrogen. A reducing gas like hydrogen should not reduce its corresponding metal, and that is also at a higher temperature. Normally many of the oxides will get reduced at a higher temperature in presence of hydrogen, but one has to choose a electrolyte in this case for solid oxide fuel cell to be successful or operating. One has to choose a very stable oxide, which is stable not only at a very highly oxidizing condition like pure oxygen, or highly reducing condition like pure hydrogen. So, this is once again a challenge, but fortunately we have that kind of a material in the form of stabilized zirconia. A zirconia is a highly stable oxide, its melting point is very high, and at the same time its non-stoichiometry is extremely low. That means, it does not get stabilized, that does not get oxidized or reduced either in the presence of hydrogen or in the presence of oxygen. So, it is that is how solid oxide fuel cell has been really a success. Success in the sense one can demonstrate at least in the lab scale that certain thing is happening. Commercial success is still to come, but many prototypes are available. Several kilowatts, hundreds of kilowatts of power can be generated from such systems. Well, next comes, there are few comparisons, in terms of the materials used, the temperature of operation, the kind of fuel one can use in different kind of fuel cell. We have already introduced few varieties of fuel cells. So, these are some comparison between them, where exactly solid oxide fuel cell stands. Is it a good one, it is a bad one in this, where exactly, how exactly it is compared with other systems of energy conversion like fuel cells. So, fuel cell is not unique that way, SOFC is not unique, there are many varieties of fuel cells. So, one should have a comparison between them. This is PAFC, the phosphoric acid fuel cell. Okay, this is phosphoric acid fuel cell. The electrolyte, as I mentioned, it is orthophosphoric acid, whereas PEM, that is the proton or polymer electrolyte membrane fuel cell, sometimes called proton membrane fuel cell. It is actually, as I mentioned, it is the sulfonic acid in some polymer, and that is the Naphion. Its trade name is Raphion, and it is produced by DuPont, and it is a worldwide famous polymer which has a sufficient hydrogen ion conductivity and can be used very easily in polymer electrolyte membrane fuel cells. And there have been extensive research whether an alternative polymer can be found out. Unfortunately, so far no other polymer has been found with that kind of properties. So, there have been some atoms, there are some other polymers available, but the performance is not as good as that of Naphion. In case of MCFC, that means the molten carbonate fuel cell, it is a molten carbonate, it is actually a eutectic mixture of lithium and potassium carbonate, which melts at a relatively low temperature, and that is the electrolyte, where the carbonate ion is the species which is conducting. And solid oxide fuel cell is basically, one can use calcium oxide no doubt, but as we have seen earlier, the yttrium stabilized zirconia has a much higher ionic conductivity or overall conductivity compared to zirconia, calcium stabilized zirconia. So, although yttrium is slightly costlier, but one can get the advantage of higher conductivity. So, yttrium stabilized zirconia is the standard material used as the electrolyte, and as we have just discussed few minutes back, that it has to be stable both at reducing as well as oxidizing conditions, and that this particular material satisfies that condition. The operating temperature of PAFC or the phosphoric acid fuel cell is about 180 to 200 degrees, whereas PEM fuel cell or polymer electrolyte fuel cell has an operating temperature of around 80 to 100 degrees centigrade, because beyond that the polymer is not stable. So, one has to limit to this kind of an operating temperature. MCFC, although it is mentioned 600 to 700, it can go up to 800 degrees also, but normal temperature is around 600 to 700 degrees centigrade, where this liquid the mixture of carbonate actually melts in a eutectic mixture. This operating temperature is normally written here as 650 to 1000. Actually, when people started using solid oxide fuel cell, the temperature of operation was quite high, about 900 to 1000 degrees centigrade, and because of various kinds of research and materials invention or discovery of different materials or development of different materials, the temperature is coming down slowly. Currently, it is about 650 to about 800 degrees centigrade, mostly 800 is the limit now. Still research is going on whether the temperature can be further lowered down to about 500 to 400 degrees centigrade. So, there are certain advantages, although some disadvantages are also there, but operating with a high temperature system is always difficult to operate, and therefore, there is always a tendency to lower the temperature. So, we have at this point a group of solid oxide fuel cell, what is called LTSOFC, that means low temperature or intermediate temperature fuel cells and so on. So, LT or IT SOFC means intermediate temperature, which is the order of about 600 to 800 degrees, whereas LT means below 600 degrees. So, there is always a attempt to reduce the temperature of operation as much as possible. Fuel, what is the kind of fuel? In all these, particularly these two, phosphoric acid fuel cell and PEM fuel cell, the polymer electrolyte fuel cell, one needs a very high pure hydrogen, very pure hydrogen, not contaminated with certain species like carbon monoxide and so on. So, this is one of the limitations, one can say, that you need very pure hydrogen to operate, because there are some catalysts and those catalysts are getting poisoned by presence of carbon monoxide. Whereas, this high temperature the MCFC molten carbonate fuel cell can operate both with hydrogen and carbon monoxide. So, there is no problem so far as the carbon monoxide is concerned. There is no platinum catalyst here. All these, both of them need some platinum catalyst. We are not going to the details why the platinum is needed, but without the platinum catalyst, very fine dispersion of platinum catalyst, this kind of system does not work. We do not need any platinum catalyst here, with the catalyst is oxide catalyst. So, this can operate with hydrogen, natural gas, even synthetic gas. So, one can generate synthetic gas from coal and then burn it. One has to find out what is the total overall efficiency. So, because efficiency is one of the driving force for developing this kind of systems. Here these are efficiencies, the bulk parts efficiencies have been put here, is about 40% here, 40% overall efficiency, 30 to 40%, and then 40 to 44% or 40 to 45 you can say, although it has been mentioned 43, 44 specifically, but it is around 40 to 45%, and solid oxide fuel cell can go as high as 30, 50 to 60. Okay. This of course has some conditions, because one has to have utility of the thermal energy also. We will look into that what exactly it means. There are few other aspects on which the comparison can still be made with the same set of fuel cells. For example, applications, stationary power systems, transportation system, as I have said, PEM, the polymer electrolyte fuel cell are primarily getting developed for the electrically operated automotive systems, and prototypes are already available for a large number of last 10 years or so. The prototypes are running in many countries, particularly in Canada and some of the European countries. Transportation systems are available. Japanese cars are also being run with PEM fuel cells. So, that is one of the driving force the application area is concerned, but in addition one can also use a stationary power, so auxiliary power systems and so on. This is again a stationary power system. Even MCFC have been developed to a large extent, almost up to 1 megawatt of power systems have been demonstrated, but commercially many of them are still not available. They are available, but it is not economic all the time. So, under specific conditions one can always use them. SOFC is being considered once again as a stationary power source because of its high conversion efficiency. 50 to 60% conversion efficiency is fairly high, and one can use it for auxiliary power systems because it contains ceramic materials. So, it cannot take lot of vibrations as well as fluctuations of temperature. So, they are brittle materials, and one has to, that is one of the major limitations. Otherwise, the driving force for developing such kind of systems is basically the high energy efficiency. These are some of the other remarks, especially markets, specialty markets due to high cost. Then getting the most attention due to its potential in the vehicles, portable power and small stationary powers less than 200 kilowatts. So, several hundred kilowatts of power station or energy systems can be has been built with fuel cells. In fact, phosphoric acid fuel cell has gone up to megawatts again. MCFC, the product focuses on commercial, industrial and institutional as well as specialty power markets. So, once again there are large number of areas or industrial situations where you need auxiliary power, you need continuous power, you need captive power. So, those things can be thought of from MCFC, and this is once again for high efficiency and low relatively low manufacturing cost per kilowatt, but running cost may be low, but power and the total overall cost is not that low. So, one has to have a question mark here. Oh, this is already going down. Well, I will complete our discussion for the class, for this class, with what are the specific advantages of fuel cells, solid oxide fuel cell in particular. This is environment friendly in the sense it does not produce NOx, SOx and particulate emissions and quiet operation, which is true for many of the fuel cells. High operating temperature, this is an advantage in some cases, and for some consideration it is an advantage because the kinetics of the process is very high. So, one can draw very high currents. Okay. So, actually current is one of the limitations in most of the fuel cells. The operating voltage or the open circuit voltage of each cell is low, it is within 1 volt, but one has to draw a very large current. So, the kinetics must be fast enough, and operating temperatures of 650 to 800 degrees are actually high temperature where kinetics is so quite fast, and therefore, one can get high efficiency. So, that is an advantage, but the operating temperature is also a disadvantage. High operating temperature is also a disadvantage from the materials point of view and the construction point of view or fabrication point of view. Fuel cell, fuel to electrical efficiency, particularly for solid oxide fuel cell, there are two situations. One is 35 to 40% without recycling of the thermal energy, and it can go up to 60% with recycling of heat, which means you see whenever this chemical reaction is taking place, H2 plus O2 equal to H2O. This has two ways of two different types of output. One is the thermal energy, it is the exothermicity of the process, as well as the electrochemical combustion. So, the electrochemical combustion or the free energy change give rise to the electrical EMF, but there is a exothermic reaction. So, it also gives rise to a lot of heat. Now, whenever that such reaction is taking place, all the energy is not getting converted into electrical energy, quite a fraction of that also goes to the heat energy. So, it continuously generates heats. So, that is also there is also a way to use that heat and maybe use it for some other purposes, not to generate electricity, but one can also generate electricity using some micro turbines, what they call micro turbines. That means the heat can be used, the combustion, the product of combustion is basically a hot gas. That hot gas can be used to generate a gas turbine or move a gas turbine, and from that also electricity can be generated. So, this is what if you combine that, okay, what we call sometimes called the combined cycle solid oxide fuel cell. So, by that recovering the heat energy also one can generate electricity, and by that the total efficiency can be as high as 60%. Okay. So, the last one is all solid state, because everything is solid, everything is high temperature stable, basically they are ceramic materials. So, they are stable, and as solid state had its own advantage, primarily the corrosion resistance. In liquid electrolytes, if the liquids are there is electrochemical reaction, and whatever is coming in contact, the cathodes and the anodes, one has to find out to choose the right kind of material, so that there is no corrosion. So, whether you talk about phosphoric acid or alkali, they are corrosive liquids, and one has to be very cautious about choosing the particular material. However, when it is all solid state, that kind of liquid corrosion is not there, but the problem will be there for high temperature. So, both the systems have its own pros and cons, but the advantage is we can have a very high conversion efficiency. Okay. So, with this we come to the end of this class. We will continue the discussion in the next class. Thank you for your attention.